In this video, we'll talk about the solutions to undamped forced oscillations and what they look like, and also how they sound, because we can also hear these things using sound. So we have our formula for the results look like, and what we can solve for the equations as long as our forcing frequency omega is not the same as our natural frequency omega 0. So in that case, we have a solution that looks like C1 cosine of omega 0 t plus C2 sine omega 0 t plus f0 over a omega 0 minus omega squared cosine of omega t. And if we take the initial conditions that y of 0 equals 0 and y prime of 0 is 0, we end up with a solution that looks like y of t is f0 over a omega 0 squared minus omega squared times cosine of omega t minus cosine of omega 0 t, because the negative of this ends up being our C1. So how can we view this function? This is a difference of two cosine waves, and it really only gets interesting when these two frequencies are close. If they're far apart, it's two sine waves and they look kind of weird, and that's just what it is. But if they are close, then we can combine these two together into a single trig function. And this follows the sum to product formulas for trig functions, which are ones that I usually have to look up for something like this. I don't have them off the top of my head. And this comes out to be negative 2 f0 over a omega 0 squared minus omega squared times sine of omega minus omega 0 over 2 t sine of omega plus omega 0 over 2 t. Now, if omega and omega 0 are very close to each other, this here is a very slowly oscillating wave. And so we can think of this sort of entire thing here as an amplitude for this faster oscillating wave. So that'll give us something like the following. I could try to draw a graph of what this might look like. And if I draw the slow wave first, I can have the slow wave that sort of oscillates like this. I'll draw its negative as well. And then I have a faster wave oscillating in between them. So just like envelope curves for underdamped, unforced oscillation, we have here a solution curve that's going to bounce between the top and bottom curves as it oscillates through. And this sort of result, what you expect to see from this case, this is beats, or the beating phenomenon. That's what you expect to see from an undamped forced oscillator where you're forcing close to the natural frequency but not at that frequency. Now, to get a better idea of what that looks like, we're going to look at this stuff in Matlab. So here in Matlab, I have some code that will do exactly this process. You'll solve the equation and see what goes on. So this is stuff that's beyond what we've talked about so far in this course. But basically, this setup here is going to solve the second order equation with a given forcing frequency. So I am going to set my omega 0, the natural frequency, which is why this is an omega 0 squared here. And I'm going to set my forcing frequency omega, which shows up on the other side here, and use it to solve the problem. Well, let's start just with a simple version of this. And instead I have this test sound here, which is just sine of omega 0 times t. So omega 0 here is 440 times 2 pi. So I can type sound of test sound, and we'll be able to hear what that sounds like. There's a solid tone. If you were at all music theory or musically inclined, you might recognize that is 440 hertz. That is the pitch for the A above middle C on a piano. Now, what I can do is I can try to solve this function where I have a forcing frequency that is close to but not quite the same as my original frequency, this A pitch. So let's see, it has different frequencies if we force at different frequencies and compare that to what happens in the general case. So we have our solid tone at 440 hertz that we just did before. Now let's see what happens elsewhere. If I force it, say, at 600 hertz. These are not really close to us. I don't really expect to hear beats. But let's see what happens if I play the sound here. That basically sounds like the two notes being played together. Right? You hear the 600 from the forcing, you hear the 440 from the natural frequency. They're sort of playing at the same time. That's sort of just what's going to happen when these things don't really interact because they're very different frequencies. And now let's try to get closer. What if I do, say, 444 hertz? If I run this one, that's the beating phenomenon we were looking for. That there, that in, out, that is the beating phenomenon we're looking for this case. And we can plot it to see what it looks like. And that's the picture we see. definitely this beating phenomenon in action in this sort of situation here. It's also what you hear in the sound from this sort of situation. Right? The same thing if you're trying to tune an instrument, you're listening for the beats in the sound wave to see when you're close to the right frequency, but not quite there. And you can adjust their tuning based on that. So that's what this sort of phenomenon is, and that's how you can see it via the graph as well as via the sound. Now, what happens if we get even closer to the natural frequency? Say I go to 441 hertz. What happens then? We still get beats, but they're slower. And if you look at the graph as well, indicated here as well, these are slower beats than they were before. And that makes sense because in the actual problem, in the solution that we found, this beating frequency, this oscillating part, the slow part, was the difference of the two frequencies over 2. So if they're really, really close together, you will see a very slow oscillating beat in this context, which is also what you're listening for when you're trying to tune an instrument. You're listening for the difference between the fast beats and slower beats you get, the closer you are to the right tuning, and then you can be good to go when you get they match and there's no beats at all. So that's what this phenomenon looks like. That's what beats are, and that's how we see them both in the solution via this slowly oscillating that multiplies our fast oscillation here, and in terms of the actual sound that these solutions make. If you were to play them and make them an auditory component, you would hear the same beating phenomenon there that you see in the graphs and the solutions that we write out analytically.